Okay, so what I'd like to talk about now is mathematical models. So a mathematical model is usually an equation, and it's an equation that fits a certain situation. In this situation, we're making soda, okay? So if we wanted to make, let's say, 16 grams of soda, 16 grams of soda, let's say we're a food science engineer, okay, and we made 16 grams of this soda. And to do this amount of small batch soda, we needed X grams of flavored syrup. I mean, we were pouring in different parts, seeing what they tasted like, the best sweetness, the best syrup quality, and stuff like that. And so we needed X grams, X plus 1 grams of sugar, and 4.5x plus 2 grams of water. And so what we're going to do is we're going to create a mathematical model, because we want, if this is our perfect combination of ingredients, we want to be able to scale it up if we want to ship it out worldwide, okay? So what we're going to do is we're going to say, okay, this ingredient, flavored syrup, X, is going to be combined with the sugar, which is X plus 1 grams, which will then be combined with the water. Let's say it's carbonated water. So it's 4.5x plus 2. Okay, and that all equals 16 grams. When you add up all these ingredients and weigh them and mix them together, you got 16 grams of your soda. Okay, so this right here is a mathematical model. Okay, so it can be used for 16 grams, or if we wanted even more, I'll show you how to do that after we do this problem to figure out how many grams of flavored syrup is going to be in this. But once we figure out how to work with this kind of equation, we can really scale it up and ramp it up, which is the power of mathematical models. Okay, so let's go here. So we got x plus 4.5x. Do you see that x and 4.5x are like terms because they all have a x in it, and just one x at that, okay? See, one x here, one x there, not x squared or anything like that. These are x's, x's, x's. So we've got 6.5 x's, okay? And then we have 1 and 2. So those are just standalone numbers. We call those standalone numbers constants because they're not being multiplied against any variable. So that's 3 plus 3. So that's 16 equals, and it's always nice to write out lines straight down there just so you can see the left and right hand sides of everything. And then why don't we try to get x by itself by subtracting 3 from both sides. That's 13 equals 6.5x. And then we'll divide both sides by 6.5 to isolate x. 6.5 goes into 13 twice. So x, we could put the x over here if we want, and then switch it later. X equals 2. Usually we like to have the x on the right-hand side, so 2 equals x, which is the same thing as x equals 2, okay? So x equals 2 grams of syrup, okay? So grams of syrup, all right? And if we're gonna have 2 grams of syrup, we're going to have, let's see, 2 times 4.5 is 9. 9 plus 2 is 11. We're going to have 11 grams of water. And then 2 plus 1 is 3, so 3 grams of sugar. So it's going to be 2 grams of syrup. We're going to have 3 grams of sugar. And we're going to have 11 grams of water. So 11 plus 3 is 14. 14 plus 2 is 16. So there we got it. We've got exactly the amounts of each of these ingredients to make the perfect mixture that we want to bottle, package, sell worldwide. Okay. So what I like to say is this line right here, 16 equals x plus 1 plus 4.5x plus 2, that's a model. That is a mathematical model. Now, it's a little bit more broken down than the next line, but the next line is a mathematical model too. 6.5x plus 3 equals 16. These two lines mean the exact same thing, except this is a little bit more condensed. So if you want to use this from now on because it's a little bit more condensed, that's fine. But just know that either of these are totally fine to work with. And so when we're asking for an equation that represents this scenario, these are two equivalent equations, and you can write either of these down because they both mean the exact same thing. Okay, now what I talked about scaling up. If this is such a great equation, and it's make sure to patent it so that no one steals it. If this is a great patented equation and you want to scale it up so you can make thousands of these grams of awesome soda to send out, this is what you can do. If you want to make the supply, I'll just deal with this second line because it's more concise, a little bit easier. If I wanted to ramp up production by 1,000, I would multiply this side by 1,000. And then I would, and this is important, and you put brackets or parentheses around everything on the right-hand side. And then I would multiply the entire right-hand side by 1,000. And then I could figure out what X is going to be. And then I could figure out what the sugar and the water is. And so I can make the same perfectly tasting soda, whether I make 1,000 batches or 1,000,000 batches, it would be the same amount of, the proportions of the ingredients would be the same the entire time. So the consistency of the product would be the same, no matter how much or little you wanted to make of it. So that is why we don't want to just find out for a particular, sometimes it's in a word scenario, word problem, it's tempting to find out, okay, how many grams do I need of flavored syrup if I want 16 grams of this total solution? It's easy to try to skip sometimes the equation and just try to figure it out without using an equation. But the skill that we're trying to get here is to come up with this equation, which we call a mathematical model, so that in the future, if you need to ramp it up by thousands or millions, you don't have to keep going back to the drawing board every time, but you can use this model. In fact, even better, once you create a mathematical model, you can put it into a computer and then just type into a computer how many times something you want, and it'll spit out the answer. But I really want us to be able to think of what we're putting into the computer in the first place. And so that is why making these equations is so important, okay?